Hello, my name is Laura Beirut, and I come from Washington University in St. Louis. And actually, this is the little preview of something else that I have to respond about drinking. And so, one of the important things is to look at all-cause mortality as opposed to mortality related to a specific disease. Because when you look at mortality related to a specific disease, what you're missing is mortality related to other things. So that Harvard paper that comes out, that Harvard group, is absolutely correct that low-level drinking reduces your likelihood of dying of heart disease. Absolutely, I'm in complete agreement. These are two large databases, the NHIS database and then VA data. And Sarah Hartz in my group has been looking at mortality based on drinking. They have a standardized survey. So it looks at all-cause mortality. So what happens is as you increase your drinking, and up to an amount that's not actually that much, you start dying of other things. You're falling down the stairs, you're having the heart disease, you're having other things. So let me just show you this. So I'm going to just point out real quick here. There are two blue lines up there. They're over each other. And that is drinking 2 to 3 times a week or less. As soon as you start drinking daily, even one drink, you do this significant tick in increased mortality. So the U.S. guidelines are actually currently wrong, saying that men could have a drink daily. The data are replicated in the VA data. Their slope is a little bit steeper. But this dotted line here is 1 drink a day daily, that blue dotted line. And then if you increase even more than that, it gets worse. And no one here is a binge drinker at all. So I just have to give that public health plot there. Again, when we saw this data, we were all really disappointed in it because this whole thought of, oh, I could sit down and have dinner and have my drink. No, sorry. Anyway. So there is this real interesting J-shaped curve, and the people who don't drink have a mortality similar to the people who are drinking daily. And what we can't figure out is whether it's because they're not drinking because there's something wrong with them, and which is an issue. So, in something wrong as in so, and it's some health problem that they have, I should say, to just be clarified. So the healthy amount looked like it was about 1 drink a week. Actually does decrease mortality even more than the people who are abstainers. And I actually think it's through socialization is what I think is actually the mechanism that's happening. Is like you go to events like this. Okay, so actually, I'm going to talk about gene and environmental interaction, and it is really on behalf of my colleagues, and go through the story about smoking. And part of this is driven, I love this slide because this really has been changing my thinking over the past year. It was a paper on breast cancer, and on the x-axis is this, what they called their non-modifiable risk. It's primarily genetic risks, so those are deciles of kind of polygenic risk scores. They were using genome-wide association over the magic threshold of 10 to the minus 8. And then they have this, the absolute risk of breast cancer is here. And that's at a population-based level, so somewhere around 12%. And then they started adding in modifiable risk factors for breast cancer. And what I took away from this paper is if you have really low genetic risk, doesn't matter all the bad things you do, you're staying under that threshold for going on to the risk. And the people who are really at the high genetic risk, the modifiable factors are playing a very strong role. So again, it's this interesting kind of way that we think about it, and thresholding makes an important difference. Again, we could different G by E interactions could occur, but this really has been kind of changing my thinking of how we intervene, how we look at people who are at risk, how we potentially screen and treat. So I always kind of think of I organized my talk in these different areas. So what is the prologue? The prologue is, if we look at death in the United States, This paper is actually from 2004, but it's pretty much the same now, is that we could look at the actual causes of death, and we get the usual suspects up there: heart disease, cancer, stroke, pulmonary disease. But what these CDC investigators did, which is really beautiful, is they went back and looked at what are the actual causes for this death. And what are the contributing factors that are leading to it? And when you look at it, tobacco is number one. So at this point, over 400,000 people die every year related to their smoking. The next groups are poor diet, inactivity, obesity, alcohol consumption, drug use behavior is down there at the bottom. But it's our behavior is driving our health. And again, this is really important to recognize this. So our behavior is also driven by our genes, as we've been talking about here quite a bit. And genetic variation drives smoking behavior. We have known for long time that smoking clusters in families. There's been these arguments: why is it clustering in families? What is the environmental contribution? What are the the genetic contributions? And family and twin studies, adoption studies, have really been focusing on the smoking, alcohol, drug use. The clustering in families is really in large part due to the genes. And so we have to also think, how do we get through these different types of to these different types of behaviors? Because thinking of a model for how you get to behavior is really important to focus us on the genetic aspects. So when we think of, we start out pristine in this world, never use, nice kids, and then we initiate our substance use. This initiation occurs, you have your first puff. My cousin thought it was really funny when he gave his other group of cousins, including me, this cigarette and watched us all choke on it. And he's like, this really environment drives this initiation to a large part. Again, there's some risk-taking involved in there, but it's what is the accessibility? Who remembers the vending machines that were there, which were just totally fun because you got to pull this handle and things. The rest of you don't know about vending machines? Oh my God, I am getting so old here. So anyway, the whole idea of being able to buy cigarettes, again, in my generation, my aunts and uncles would send us to the store to buy their cigarettes for them. So we've really had this dramatic change in our environment and this accessibility. So after you have your first puff, you transition to become a smoker. And a smoker is really defined as when you smoke 100 cigarettes. And this seems to be a magic number. And in part, this is getting recorded, right? Okay, I'll tell the story later. This is a magic number. And once you surpass this number of 100 cigarettes, 85% of people go on to become a daily smoker. So this is a really important number to know if you are a manufacturer of cigarettes, because that means you only need to give away 5 packs before you have someone who is a committed smoker. This is really a very important number. And then we have this transition of going from a lifetime smoker to nicotine dependence. And biology really is driving this aspect. This step here is actually the most biologically driven and genetic step of in this transition. So the common test that we use is this Fagerström test for nicotine dependence, developed in Sweden, and two characteristics drive defining who's nicotine dependent. It's how soon after you wake up do you have your first cigarette. The sooner it is, the more addicted you are, and then how many cigarettes do you smoke per day? Most of the GWAS have been done on this cigarettes smoked per day, which is wonderful, great, it's a major component, but just recognize it is just one component of addiction. So in the early 2000s, we did a population-based screening of 2 cities, Detroit and St. Louis, where we screened over 50,000 individuals when people had landlines, and we targeted individuals who were between the ages of 25 and 44 years of age and surveyed them and asked these specific questions about the steps. How many of you had initiated smoking, even a puff? Only 50% of the population had at that point in time. Great public health news. How many then if you've initiated, did you go on to become smoke 100 cigarettes? 58% made that transition. And then if you smoked cigarettes, where were you with nicotine dependence? And what we see is actually the largest group becomes nicotine dependent. Another third have some symptoms of nicotine dependence. And then there's this special group, this chipper group, it's often called, which is less than 20%, who have no symptoms of nicotine dependence. They never smoked more than 10 cigarettes a day. They could give it up at any time. They don't have any problems. You'd hear descriptions like, oh, I smoke after I have dinner, or I smoke only when I golf, or whatever. It's these kind of light smokers who all of us would have called a smoker in the smoking field, but they seem to be resilient. And so more than a decade ago, we did our GWAS where we recruited people from these two extremes, current nicotine-dependent people and this kind of magic group who is not dependent. And we got hits in it. And our major hit was in the chromosome 15 region. This was followed by a large-scale GWAS led by Wade Berrettini, the other by Decode in 2008, which confirmed our work, and then the large-scale GWAS in 2010, which again confirmed what was going on. And here is the Manhattan plot. And what you see here is it's a Dubai plot. What we have is a really strong signal for behavior on chromosome 15. Again, there are other things kind of, floating around below that, but chromosome 15 is really driving it. We affectionately call this the Mr. Big finding because Sex and the City was popular then. And right under this finding is the nicotinic receptors. I mean, it is like so beautiful. These receptors actually were not being studied at all at this time because these were less common nicotinic receptors. So again, they didn't make it into the candidate gene groups. But when you see this and you kind of get into it, it's like, oh, God has like shone down upon us and blessed us with this big signal. Right over the nicotinic receptors. I'll tell you there's an amino acid change in the alpha-5 nicotinic receptor. There's tons of biology we've done. That variant is functional. It's when it's present across other populations, it increases the risk. Lots of work. This is like we are on the right variant. It's not only that variant, though. There's expression changes occurring here. There's a lot going on in this region. So, anyway, we have been running with this group, this nicotinic receptor cluster, and kind of moving forward with it. So I think that smoking behavior is in some ways like Alzheimer's disease. You have the ApoE finding for Alzheimer's disease with this really strong peak. With nicotine dependence, you have this very strong peak in the nicotinic receptors. With alcohol dependence, you have a very strong peak over the alcoholism receptors. And so again, we have these very strong biological, kind of natural targets, and then we have this kind of other stuff that's lower down. So we've been moving forward looking at the interplay between genes and environment. And one of the things that we wanted to look at was, well, what happens when you treat people? This is really kind of like the holy grail of what we want to do. These variants are common in populations of European ancestry, not common in African Americans or Asian populations, but it is, I think part of the reason we found it is because it is present at such a high frequency. Somewhere around, the risk allele is present around 30% of the population. And this is an interaction, a pharmacogenetic interaction. What you see is there's a group treated with pharmacologic treatment in the green, and then the patients are just received counseling. They received a placebo medication. And you see if you have the higher risk variant, your likelihood of successfully quitting smoking goes down. Just makes sense. Kind of the definition of nicotine dependence is your inability to quit. So, the biology, again, is working. The story is great. And what's beautiful about this is we could ameliorate this genetic risk with aggressive pharmacologic treatment. So then everyone has the same risk factor. So Lucian Chen and my group published this, and we got a nice letter to the editor that they said, you really kind of should have presented it this way, which is number needed to treat. Who knows what number needed to treat is? Okay, so number needed to treat is this wonderful way to look at things, because part of it is this interpretation. A perfect number needed to treat is 1, which means you treat an individual who has a disease, whatever it is, and how often does that person respond? So do you have to treat 1 person to get a response, or do you have to treat 10 people and really only 1 benefits from the response? So the best number needed to treat in medicine is for H. pylori. It's the bacteria that's in your gut, gives you ulcers, and moves forward with its number needed to treat is about 1.1. We have a number needed to treat of 4, which is amazing. Hypertension, number needed to treat, is about 30. If you think about many of the other treatments, the number needed to treat is often in the hundreds, 200s. So this really is showing that if you have this allele, which is fairly common, you are really responding to replacement therapy, nicotine replacement therapy, pharmacologic treat. And basically, if you have the low-risk genetic variants, you're not responding. So it, again, makes us think we should be targeting one group. We need other pharmacologic treatments for the other. We looked at another interaction, which is age of onset. So when you initiate smoking earlier, you are more likely to be nicotine dependent. We looked at this one genetic variant, and this risk, it changes based on, the genetic risk changes based on your age of onset. So we dichotomized those who started smoking before 16 and those smoking at 16 or later. And we could see, again, the late onset group. We have the reference, low risk genotype, and late onset. And we could see that the genetic risk is increased with this earlier onset. Again, moves with the biology where we think that the developing brain is in particular susceptible to all addictions. So my colleagues have been, we've been working on the health retirement study and looking at socioeconomic status. And this is, socioeconomic status is a composite of several characteristics while the individual was growing up. You guys know this data set much better than I do. But we see an interplay with this childhood socioeconomic status and the polygenic risk score. So we've moved into, with my colleagues, we've moved into the polygenic risk scores. We see the polygenic risk scores predicts heavier smoking, high socioeconomic status predicts lower levels of smoking, and there is this interaction. And to visualize it, we could see the amount that people smoke. So it's really relatively flat based on your polygenic risk scores if you're in the higher socioeconomic class. But the genetics really is kind of expressing itself much more fully in the lower socioeconomic groups. So again, my interpretation of that is that we're able to overcome some of our biological risks when we have more resources. So I just want to kind of move into cancer, that this is just totally loaded with G by E all over the place. So the genetics of lung cancer and other smoking-related diseases, the strongest genetic risk factors are the genetic risk factors of smoking. So with taxation, we have per capita smoking, cigarette consumption in the US. Thank you for taxation. Here's the lung cancer death rate. Oh my gosh. I mean, it can't be more beautiful than that. It almost, look at these, how these curves match. There's this delay, but we see it, and we anticipate that the lung cancer rate is going to continue to go down. So in 2008, they started their first GWASs of lung cancer. It was followed by COPD, and what we see is chromosome 15 right there. The lung cancer people thought they were going to find biology related to lung cancer. What they found was the biology related to smoking behavior. And so the strongest genetic contribution to lung cancer, COPD, is this contribution to behavior. They call it actually a G by E because the genetic effect, it has no effect for lung cancer if you don't smoke. And so really it's all mediated through smoking. So just, there was some talk about, what's your percent variance explained? And I wanted to just show this. If we take, what's the percent variance explained by, the Mr. Big area of cigarettes per day, it is a little less than 1%. But you have to kind of look beyond that. So this variant actually drives how much you smoke, how deeply you inhale each cigarette, and it is associated with this delay in smoking cessation. So having the high-risk genetic variant delays your median smoking cessation by 4 years. So there's this cumulative effect that you're having. It's not only cigarettes per day, it's how heavily you're inhaling each cigarette. And you have multiple years of increased smoking. So this is really having this much greater contribution to disease. It also has this effect of the age of diagnosis of lung cancer. So if you get lung cancer, it actually drives your age of onset of diagnosis down by 4 years, which has important implications because we're now screening for lung cancer. And should the high-risk people be screened at an earlier age? So human behavior is complex. There's G by E all over the place. We see it with alcohol metabolism. I loved that example of this strong genetic effect with blood pressure. Actually, there's a G by E with those who have these variants that affect metabolism of alcohol. If amount they drink actually influences their cancer risk. And this interplay is through so many different environments. We have to think of the environments in wide ranges, and now we're seeing this issue with socioeconomic status, and we anticipate it's going to contribute to the ongoing disparities we have. So thanks to everyone who's contributed.
Okay, it's a pleasure to be here. This is a paper about wealth inequality in the United States, co-authored with Danny Barth, affiliated with CESR here, and Nick Papageorge at Johns Hopkins. A topic that a lot of economists have cared a lot is the large inequality in wealth in the economy and its growth over time. You can measure this in a bunch of different ways. Here's a plot of one particular measurement. Since the 70s, wealth inequality in the United States has grown substantially, something that we care about because it maps into welfare, resources, et cetera. Now, a parallel trend, a parallel inequality that you might think explains a lot of this, and it does explain a lot of this, is inequality in labor income. Inequality in earnings, what I earn directly translates into resources I can accumulate in terms of wealth. However, that's not the end of the story, and in fact, labor income inequality alone has a hard time explaining the cross-sectional variance of wealth that we see in the economy or the growth in this inequality over time, and that's led macroeconomists to look at other explanations, variability and other factors that might explain this dispersion of wealth, things like variation in bequests, variation in risk preferences, variation in business ownership or entrepreneurship, and there's always something kind of missing. A recent set of papers has argued that something that you might need is heterogeneity in the population in the rate of return that you can access to wealth. So work by Ben Habib and Bissin and co-authors has shown kind of theoretically that to get the kind of fat tail in the wealth distribution, you might need above and beyond variability in these other factors, variability in the rate of return you get on assets. Take two households, same level of assets, same inflows, one household's getting a greater return in asset markets. This is also validated by some recent empirical work that suggests that returns are variable and that these things seem to persist over time. So as you can see, that might be an intuitive idea, something that makes a lot of sense, but only very recently have people had data because of accessibility of large administrative data sets on wealth to kind of demonstrate this empirically and show that it's sort of important for explaining heterogeneity in wealth. But these results take the form of fixed effects, that there are some permanent differences across individuals or across households in rates of return to wealth. That leaves unexplained the source of these fixed effects or the mechanisms through which they might operate. And so I think that's where we kind of step in and say, well, it's possible that the reason why some households have persistently different rates of return on assets and therefore different levels of wealth is because of factors that might be related to human capital accumulation, things we might be able to measure through this genetic score for education. So that's going to be our question. Are the genetic endowments captured in the kind of EA2 score that everyone is very familiar with at this point, are these able to independently predict wealth above and beyond completed schooling? And does that hold some clues as to what kind of persistent characteristics across people might drive heterogeneity and the returns to wealth? So in this paper, we're going to examine this in the health and retirement study. We're going to examine this with the LD Preds version of the EA2 score that a lot of you are familiar with. And that's going to be our basic question. So controlling for education, we're going to observe a substantial association between these genetic endowments and wealth, and then we're going to try to dive into what mechanisms might rationalize this with the eye of, say, building, informing how we model heterogeneous agents in the macroeconomy. What kinds of heterogeneity do you want to build into these models to be able to have good, accurate models of the sources of inequality? So what are we going to find? Something that maybe is not surprising. Well, maybe it's surprising, maybe it's not. A higher polygenic score predicts higher wealth, even controlling for completed education. A 1 standard deviation rise in the score, caveats to the presentation of the standard deviation, is associated with about 10% higher wealth after controlling for education, parental education, a host of background controls. And we're going to find that this gradient is not fully explained, not even kind of substantially explained by the usual suspects that you might throw into such a model. So flows like income, we can observe that in the 50s for these households before they retire, and you can transform that in a number of ways. That doesn't seem to explain much of this, nor do sort of bequests or inheritances. You might think a big linkage is that my parents had these genes, they were wealthier, and they passed on wealth to me. All of these things make a difference for household wealth, but it doesn't really seem to explain much of this gradient. One factor, which is an endogenous choice, not a kind of persistent factor of an individual, is whether or not these households are participating in the stock market. That does seem to mediate a big chunk of this genetic relationship. But then the big question then is why, right? Because that's an endogenous choice. I have to take a step back and ask what's causing people to sort of make different choices in asset markets and participation. It could be risk aversion. That's an obvious mechanism. We have some noisy measures of risk aversion in the HRS. To the extent that we can measure it, that doesn't seem to play a big role. Financial literacy, we have very small sample sizes, so we have some results on that. But two factors that we can measure that seem to make a big difference are the kinds of expectations that you form about macroeconomic events. We're going to find that individuals with higher values of the score tend to have more objectively correct beliefs about probabilities associated with macroeconomic events, like the probability that the stock market goes up or the probability of a major recession in the United States, the probability of double-digit inflation. And there's much less heaping on extreme kind of incorrect beliefs. Much fewer people, there's a strong negative association between the EA score and the probability that I say there's a 0% chance with confidence that the stock market goes up, or there's a 100% chance with confidence that we're going to get double-digit inflation. We also, and this links in, Dan Belsky and Ben Deming had some work where they stress kind of planfulness as one mechanism. We're going to look too that's something that we find is an important mediator of this relationship between the genetic score and household wealth, and that this is something that might, that also plays a very important role. We're going to find as well that if you think that people are making systematic mistakes, if they have low values of this genetic score in how they manage finances or how they make choices about portfolio decisions, it might be the case that if you remove some amount of autonomy from those individuals, these genes would matter less. One, this is not a perfect natural experiment, but something we can observe, are whether or not having a defined benefit pension makes a difference, right? If I'm getting a check every month from my employer that doesn't require me to balance a 401k, doesn't require you to make financial decisions, that will substantially reduce this gradient. We can talk about that again. So what is our contribution? Our contribution is not to show that there's an association between these scores and later life kind of outcomes. There's other papers, our own work by Dan Belsky and Ben Deming that demonstrate that. We're trying to dig into the kind of mechanisms of what links economic primitives, things like risk aversion, which we don't find, or like how you form expectations to the ultimate gradient in wealth. And this is going to link up with some very recent work on a genetic basis for savings. A well-received paper in economics, a twin study by Cronquist and Siegel, demonstrates a kind of heritability of savings, a genetic basis for this. And they're going to suggest that self-control is important because they find genetic correlations between savings behavior and smoking and obesity. And they actually find no genetic correlation between savings and education. We're going to show something a bit more nuanced, right, which is that you get to wealth through multiple mechanisms, not just through saving more, but also through access to better investment technology. So their results are perfectly true. We're finding some nuance to that as well. There's another set of genetic pathways that impact household wealth that may go through the kinds of investment decisions and investment technologies that you can access. And if I ever get to the end of these slides, forgive me for the rate at which I'm talking, but I'm hoping to tell the complete story. We can get polygenic scores for BMI, cigarettes per day, et cetera. They're going to predict household wealth independently of the EA score, and they're not going to have associations with these belief variables, which strongly suggests to us that there are different, distinct mechanisms, genetic mechanisms, some of which might work through kind of self-control that's bound up in choices like smoking or overeating, and some choices that might work through specific cognitive pathways that deal with belief formations and expectations. This is related to a bunch of literature, some of which I've already noted in the genetic space. Forgive me for time constraints. I'm not going to go over it in detail. We're going to use the health and retirement study data, which many of you are familiar with. We're going to look at we're in the genotype sample. We're going to restrict to genetic Europeans in certain age range. We are going to restrict our sample to households where basically everyone is retired. Now, there's a very specific reason for that. We're going to construct a wealth measure that sums up a broad category, as best as we can, all sources of household financial wealth. That includes not only things like savings and assets you've invested, but also housing wealth, and importantly, pension wealth. And this is a really important part of the story, because the off-the-shelf RAND HRS files that you get don't automatically include defined benefit pension wealth or even some classes of defined contribution wealth. And we went through a torturous process last summer, or at least Danny Barth did, of cleaning that data and constructing good measures. But we have to restrict to households that are retired in order to correctly impute values for certain of these categories. Many of our results survive different cutting of these things, but the moderation of the genetic score with defined benefit pensions is something we could only have learned by putting in this effort to really get at the contribution of defined benefit plans to wealth. The wealth distribution looks not insane. It matches quite well with work that like Jim Paterba has done on this. And if you just think of the unconditional association between the EA score and household wealth. This is the EA score of the financial respondent. There's a whole complicated set of questions about whose score inside the household matters. I'm not going to talk about that today, but we've done work in the paper that addresses this. This is the score of the financial respondent plotted against, non-parametrically against household wealth. A massive association on a log scale. This is an utterly enormous relationship. Of course, much of this is mediated by educational attainment, right? And so we're going to show you a bunch of regressions. We're going to include some standard controls. These are going to be panel regressions. We're going to have principal components. We're going to have a bunch of standard things, including parental background, dummies we're going to dummy out missing values of father's, mother's education. I know Lauren was talking much about that yesterday. And we're going to cluster standard errors at household level, lots of standard things. And what do we find then? Well, if you just have a kind of unconditional regression, no controls for respondent education, parental education, a one standard deviation increase in the score associated with an increase in log household wealth of about 0.23, massive kind of differences. When you control for completed education, a lot of that goes away. A lot of that is sort of soaked up. Controlling for parental education leaves this big chunk, though, that remains to be explained. This kind of gradient, a one standard deviation increase in the E8 score is associated with about a 10% increase in household wealth. That's still a big kind of gradient, and we have something to explain here. Okay. we don't, what is the kind of incremental R-squared of the EA2 score to this? Not that much. If you don't include own education, about 2.2%. If you condition on education, about 0.4%. That's a small but non-trivial number. I mean, the dispersion in wealth is kind of enormous and very kind of noisy, so I'm not too concerned about this. I still think we're learning something useful and interesting about some of the main genetic markers that seem to be associated with human capital accumulation. We're going to do a set of exercises here where we just take our basic regression and sort of add a bunch of controls for standard mechanisms that you think might link the genetic score to household wealth. So things like income, things like bequests that you're getting from parents, things like business ownership, et cetera. And we're going to kind of demonstrate that these explain some of that gradient, but a lot is left to explain. So in column 1, we're now conditioning on a sample that's consistent. So this 12% figure looks a little bit different than what you saw before. That's because we're restricting the sample to include a comparable set of people across all these specifications. The order in which you add these things always matters, so I wouldn't interpret column to column changes too much. I would jump right to the 4th column. If we include, to the best we can, measures of income observed in the 50s for these households, we look at the running sum of log inheritances, a dummy for whether you've ever received an inheritance before and after, whether you ever owned a business. All of these things are highly, highly associated with household wealth. But it does, and it explains some of this genetic gradient, right? The difference between, say, the coefficient we have in column 1, coefficient in column 4, that's not nothing. That's a chunk of this. If you add a single dummy for whether or not you own any stocks, that cuts this thing like about in a third, right? Going from this kind of 9.8 to about 6.1%. So and that, if we can bootstrap that, there's a significant kind of reduction in the size of that gradient from column 4 to column 5. So stock market participation seems to be an important mechanism for explaining this. And you could, obviously, we're going to, if those are our results there, we're going to find a positive association between the genetic score and stock market participation. That survives controls for the lag of past wealth. If you thought this was just capturing a kind of nonlinearity, that the wealthier households are, the more they're just likely to have stocks. Even if we control for sort of the lag of wealth, we get this as well. So then, why? What's the kind of what explanation might we have for this? Well, one obvious candidate would be something like risk aversion. I've just gotten the signal that I have 5 minutes left, so I'm gonna jump through this because there's some interesting things I wanna show. We have a noisy measurement of risk aversion in the HRS. The EA score is negatively associated with that in this kind of binary make. It doesn't really explain this gradient. We could go on, and we might think financial literacy is important. We don't have very big sample sizes, so I'm going to skip over that. Expectations might make an important. So this is the heart of our story, this and this kind of financial planning horizon. There are sort of 3 questions that are asked. Probability that the stock market goes up over the next year, probability that the US has a major economic recession, the probability of double-digit inflation. What are we going to show? Obviously, there's a lot of heaping, say, at 50-50, but we also have masses of people that give these sort of really extreme beliefs that have kind of no chance of being right. There's a 0% chance that the stock market goes up. There's a 100% chance of double-digit inflation. And what do we find? That across all 3 of those outcomes, a higher value of the genetic score is negatively associated with just an absolute deviation of your elicited belief away from an objective belief that we can sort of feed into this. And it's negatively associated with the probability of giving a kind of extremely incorrect belief of 0% or 100%. Note, however, it's not associated with just the big spike of 50%. So this is not a story necessarily about heaping in general, that people are, there's more measurement error in their kind of beliefs, and they're just going to these heaps more. No, it's specific heaps that matter, and ones that lead you in the direction of 100% certainty of kind of either direction. This could just be measurement error, right? It could just be that people with lower values of the score are more prone to sort of bouncing around. It doesn't actually affect their household decision-making process. That's not what we find. These beliefs matter in the sense that they map in to the choices that individuals make and to the kinds of household wealth outcomes that we observe. And in surprising ways. So someone who is 100% sure that the stock market's going to go up actually is in a household that has substantially higher wealth. Right? These are on average people that have lower values of the score, but their kind of incorrect belief is, is pushing them in the direction of participating in the stock market in the face of maybe other frictions to this. This planning horizon variable, I'm planning for family saving and spending, which of the following periods is most important to you? Next few months, next year, next few years, next 5 to 10 years, longer than 10 years. We can interpret this in two ways. This could be time preference. Right? This could be a variable that captures, do I care, just in a utility sense, more about the present versus the future, or this can capture something about the ease with which people make forecasts about future events and the ease with which they can kind of integrate out kind of future streams and make decisions in that way. So a very recent paper by Gebex and Leibson develops a model where you can take individuals that they care the same about the present and the future, but if they differ in terms of how precise their beliefs are about future events, that will generate behavior that might look like myopia just based on difficulty of kind of processing beliefs. That financial planning horizon matters greatly for wealth. It matters greatly for stock ownership. The EA score is positively associated with a longer financial planning horizon. We don't think this is related to just pure time preference because we have some questions in the HRS that would allow us to kind of get crude estimates of your annual discount factors. We don't find, except for the most patient category, that there's much of a difference across these things. And furthermore, a discount factor of 0.7 is not consistent with, I only care about the next few years as well. What do we find? That if we start with a consistent sample and we add in both the belief controls and the planning horizon controls, we account for, I think, a big chunk of this gradient. It's something about like 20%, at least as much as you would account for with the standard household controls of income and these kinds of flows. And I know I'm almost I'm out of time already. One thing that moderates this, just indulge me for 1 second, is if I have a defined benefit pension plan that kind of unburdens me of some amount of financial decision making, that substantially interacts with this genetic score, and it cuts the genetic gradient by about half. And it doesn't seem like there's terribly much selection, at least on observables, into defined benefit pensions. There's no association with the genetic score. So it seems like that's a mechanism that matters. And then I already said these results for BMI and for smoking already. BMI and smoking polygenic scores predict wealth pretty substantially. They don't have any association with these kind of deviations from beliefs. That strongly suggests some separate mechanisms that might be at play. So that's it. Thank you for letting me go over time and listening to me spout on in excited tones like a madman. But that's what we have.
Good morning, everyone. My name is Lauren Schmitz. I am currently an NIA postdoc fellow at the University of Michigan. I'm also a postdoc with the Health and Retirement Study, and it's really great to be here today. I'm going to present some co-authored work with Dalton Conley on the effect of Vietnam-era conscription and genetic potential for educational attainment on schooling outcomes. So our overarching research question here is, was the post-war education of Vietnam conscripts moderated by genetic influences? There's a really robust literature on this in economics and sociology, and prior studies have shown and that have used the random nature of the draft lotteries to identify the effect of Vietnam-era GI Bill on schooling. And these studies have found that the GI Bill increased the post-secondary education of veterans by approximately 0.2 to 0.3 years. So in this study, we ask, does the impact of the Vietnam draft on schooling differ by genetic propensity toward educational attainment? Past studies have really only been able to estimate the local average treatment effect of conscription on schooling at the mean, so kind of at the average genetic point in the distribution. And there we see very small effects, as 0.2 to 0.33 years. And another big motivation for this study was kind of as a proof of concept. So we wanted to see if you could use polygenic scores and an environmental shock in early adulthood to measure the impact of gene-environment interactions in observational data. And along these lines, this is kind of something we wanted to do because we saw this growing endogeneity problem in a lot, not all, but in a lot of the applied gene-environment research that was emerging, especially with using polygenic scores. And just to kind of give you an example of how this might play out in our case, for this study, we're really interested in how the polygenic score is associated with educational attainment, of course, as everyone else is, and how this is moderated by veteran status. We know from prior studies that there are a lot of observable ways that veterans and non-veterans may differ, and that raises concerns about unobservables that we systematically can't observe that might be correlated with education and bias our findings. So just kind of classic omitted variable bias there. And when we throw the polygenic score into the mix, we have additional endogeneity concerns. So there could be correlation between education and unobserved genetic influences. And here I'm thinking mostly of population stratification. So it could be differences in allele frequencies between subpopulations are spuriously correlated with educational attainment. And then another issue with the polygenic score is that it could be that people are selecting into veteran status because of their genotype. So this would just be a classic gene-environment correlation. So when we add the polygenic score into the mix, it kind of just really enhances a lot of the endogeneity problems that we already had when we were trying to estimate the impact of veteran status on education. So we really stress the need, especially for this study, to really, we need both G and E to really be independent of each other to properly identify gene environment effects. Another kind of proof of concept or thing that we wanted to really communicate with the study is that gene-environment interactions are a really fruitful way to integrate genetics into economic research. So even before we interact the score with anything, as Dan mentioned and talked a lot about yesterday, just including the polygenic score as a control can really increase the precision of our estimates, which can reduce the power that we need to detect effects. And so this reduces variation in unobservables, and it can also help balance our treatment and control samples, for example, in an RCT setting. But we can also use polygenic scores to identify heterogeneity in treatment effects. And I'm going to argue that it's a better measure to at least start to examine heterogeneity. We know that heterogeneity is the response, the norm to a treatment or to any sort of environmental exposure. And so I'm going to argue that it's a little bit better of a measure to use to explore heterogeneous treatment effects than something like IQ, which is very endogenous to the environment. So it's this kind of exogenous source of inter-individual variation that's really stable over time. And with the polygenic score, we're also really maximizing statistical power, so we can incorporate it into small studies like the one we're going to use today, where we have a very small sample of veterans. And that's something that others in this room have discussed, and so I just want to acknowledge that. And I think it also really strengthens claims of external validity. If we have a large enough sample, we can start to make inferences about how a given treatment will affect the entire genetic distribution. So we can really see how a treatment might, the larger scale implications of it, and that might help us with external validity. So now moving on to this study, what we do is we use a data set that combines sociodemographic and genotype data from the health and retirement study. I'm sure everyone in the room is familiar with the HRS, but in case you're not, it's a biannual, multidisciplinary, nationally representative longitudinal study of individuals over the age of 50 and their spouses. It began in 1992, and they're currently out there in their 2016 wave, interviewing a new cohort and other prior respondents. In 2009, the HRS genotyped over 12,000 respondents who provided DNA samples from saliva in 2006 and 2008. And what we're going to do is link that genotype data version 1, those 2006 and 2008 samples, to both HRS public use data and to restricted date of birth files to code for draft eligibility. And I'll talk a little bit more about that in just a minute. So our final sample consists of 504 white non-Hispanic men born between 1948 and 1952 from the 1992 to 2010 HRS waves who were genotyped in 2006 or 2008. Our measure of genotype in this study is, of course, a polygenic score for educational attainment. I'm not going to go over how it's constructed. I think we're all familiar with that in this room. But the beta that we use here to construct our polygenic score is from the Education GWAS 2.0 that was conducted on individuals of European ancestry. We do utilize beta weights that include 23andMe and UK Biobank, but exclude the health and retirement study. And so because we do use that restricted data, the polygenic score was constructed by ISU and generously shared with us using the software LD-Pred and all available SNPs. And so there's approximately 1.4 million SNPs that overlap between the GWAS and the HRS genetic database. So one thing that I wanted to highlight was that if we look at the incremental R-squared or the semi-partial R-squared values, we find that it's much higher in our Vietnam veteran sample than it is in the HRS overall. So here we can see, let's see if this clicker works. Okay, so here we can see this is the overall incremental R-squared in the HRS genetic sample. This is for women, for men overall. And this should say Vietnam veteran sample, so it's not just the Vietnam veterans, it's everyone in our sample. So this is vets and non-vets born between 1948 and 1952. And you can see we have an incremental R-squared of 14%, so that's quite high. So this is kind of preliminary evidence that something was going on in the environment to induce high polygenic score men to either get more education or that among men who were drafted perhaps to get more education through the GI Bill. So perhaps it also lifted the financing constraint for a lot of those high polygenic score veterans. So I just thought this was kind of an interesting first pass at the data. And if we break this down into draft eligible and not draft eligible individuals, we see there's no difference in the incremental R-squared. So that was encouraging for this study. So our environmental effect that we're using is the Vietnam era draft lotteries. The random nature of the draft lotteries has been used as a quasi-natural experiment to identify the impact of Vietnam era service in a host of studies. Here you can see Representative Alexander Perney drawing the first capsule in the lottery drawing that was held on December 1st, 1969. The capsule contained the date September 14th. So if your birthday was September 14th, you received a random sequencing number of 1. This was done until all the dates in the year had been drawn and assigned a random sequencing number. Does anyone have the birth date of September 14th? I always ask this, and I have yet to have anyone raise their hand, but you would have been out of luck. You would have gotten a random sequencing number of 1. And so that was the first wave of the draft lotteries. That was in December 1969. That was for the 1944 to 1950 birth cohorts. And they called random sequencing numbers at or less than 195 for their manpower needs. In July 1970, they had a second wave. That was for the 1951 birth cohort. And in August of 1971, they had a third draft lottery. There was a draft lottery in February of 1972 for the 1953 birth cohort, but those individuals were never called to service. The education phenotypes we're going to be looking at are total years of education, total years of college education, and then dichotomous variables for whether responded completed each degree level. So we look at GED or high school plus. That's if you have a GED or high school degree, you get a 1, no degree 0. Then associate's degree plus, so associate's degree or higher gets a 1, GED or high school degree gets a 0, and then so forth for bachelor's degree plus. And we model it this way so that we can capture the gene environment impact at each level of degree completion, instead of the average overall previous transitions. So here's just showing some basic descriptive statistics by veteran and draft eligibility status. And first, I just want to direct you to this column here highlighted in red. And you can see there's a significant difference both between the polygenic score and the years of education and all of our other educational phenotypes between veterans and non-veterans. And in fact, veterans on average have a lower polygenic score than non-veterans. So this is concerning for us, and we were then, of course, very relieved to see that when we look at the draft, we compare the means between the draft ineligible and draft eligible samples, there is no significant difference in the means. So this suggests that those kind of random samples are still balanced in the HRS. And that was a concern. We were looking at these vets and non-vets, this birth cohort, they were genotyped between the ages of 56 and 60 in the HRS. So it's definitely a concern that there could be mortality selection, attrition bias, or just even bias by genetic screening consent. But what we see here is that the two samples were still balanced. We use an IV two-stage least squares approach to estimate the gene environment effect. We treat veteran status and its interaction with the polygenic score as endogenous. So here we have education regressed on veteran status, its interaction with the polygenic score. And then in the exogenous X matrix here, we have the main effect of the polygenic score, which we're treating as exogenous, the month and birth year dummies, and then the first 4 principal components. So then we use draft eligibility as an instrument for veteran status in the 2 first stage equations. So we instrument veteran status with draft eligibility, and its interaction with the polygenic score with draft's interaction with the polygenic score. And what we find is that military service reduced the schooling of below average polygenic score veterans. So here's just a table of the local average treatment effects of veteran status at select polygenic score values. We did standardize the polygenic score. And what we find are the effects are all happening below the mean. So you can see here that veterans 1 standard deviation below the mean completed 3 fewer years of schooling than non-veterans with a very similar polygenic score. This kind of seems to pan out to about 2 fewer years of college education. We do not find any effects for GED or high school, which was really great because that was kind of our placebo test. Veterans weren't drafted until they were 19, so the vast majority of them had finished high school. We don't expect, therefore, the draft to have a treatment on the completion of high school, so we did indeed replicate that. And then we find that having a polygenic score below 1, being a veteran, added up to about 70% fewer likelihood of completing an associate's degree. And then, so these are these same results graphically, and here you can see that this is the difference in predicted years of education between veterans and non-veterans across all values of the polygenic score. So we have values of the polygenic score on the x-axis, and then predicted years of education on the y-axis, and you can see significant differences kind of right as we get just kind of about 1 standard deviation and below. So then out of curiosity, I thought, okay, well, I want to take a look at these same results within the context of kind of the naive OLS model. So if we just interact the polygenic score with veteran status, what are the comparable results? And what we find are the estimates from the OLS model show effects going in the completely opposite direction. So this would indicate that it is important to think about how we're modeling the environment when we're looking at these interactions, because these are very different results and would have, I think, very different policy implications were we to, be looking at policy implications from a study like this. Thank you. So just to wrap up for the discussion, we find effects of Vietnam-era conscription on post-war schooling do vary by genotype. We find that veterans with a polygenic score 1 to 2 standard deviations below the mean were 70 to 90% less likely to obtain a post-secondary degree than comparable non-veterans with the same polygenic score. We do not find a significant effect for conscripts with an at or above the average polygenic score. Some limitations of this study: we can't really describe any sort of underlying theoretical relationships between military service and schooling that might have limited the long-term socioeconomic attainment of veterans. So, for example, PTSD or number of tours, whether or not they were in combat. So we can't assess any of those things. And of course, because of that, there's also, because we're doing IV, there's also weak external validity. So these results can't really be generalized to the population as a whole. So they're very specific for this birth cohort that we're looking at for the Vietnam vets. In terms of implications for policy and research, and I kind of mean more broadly based on all of our studies and kind of what we're looking at, not just for this study in particular, it seems as though this feedback between G&E is really enriching our understanding of social inequality. Genotype itself seems to be a moderator of social inputs that generates hidden forms of inequality. And so I think it can kind of be this very sensitive indicator of how the social environment may be engendering inequality. So I think in a lot of our studies, if we're seeing a very strong genetic gradient emerging, that's telling us that there's something going on within the social environment that's kind of inducing that kind of inequality by genotype. I don't think it's a good sign to see that, because we know that educational attainment, these things are so much environmentally determined that if we see a strong genetic gradient emerging, I think that's kind of a sign that something's going on in the environment that we should look a little bit closer at. So I think then it also improves our understanding of socioeconomic disparities and the distributional consequences of interventions. It seems a better socioeconomic environment can really increase returns to genotype. And here I want to highlight a study, the other study by Kevin Thom, he didn't talk about today, but I think a really interesting one that shows that the distribution of the educational polygenic score is remarkably similar across childhood SES categories, but individuals born into a high SES environment are more likely to complete college regardless of genotype. And so I think those findings kind of dovetail with ours in the sense that it seems that people with the lower polygenic scores who were exposed to a more disadvantaged environment were the ones who experienced more disparities in educational outcomes. But overall, I think a lot more research is needed to identify how genetic attributes modify the effect of the social environment across the life course. I know that's the interest of a lot of us in this room, and so it's really exciting to be here and give this talk in front of you guys. And I think for me, a big question is, can interventions during sensitive time periods really reduce disparities in health and socioeconomic attainment? So just want to say thank you, a big thank you to our funders, the National Institute on Aging, the Russell Sage Foundation, and to Tita, Stan, and David for inviting me here to present and for putting on this great conference. So thank you.